Okay, I think it's time to start the second session of this morning. So in this session, we're going to have 3 speakers. The first one will be Professor Shi Jianlin. Professor Shi obtained his PhD degree in 1989 in Shanghai Institute of Ceramics. And he was selected as an academician of Chinese Academy of Sciences. He had been working on the processing science of advanced ceramics and the sintering theory of advanced ceramics before 2005. Most recently, he has proposed and been focusing on the nano-catalytic medicine for the treatment of malignant tumors and other serious diseases by using non-toxic or less toxic nanomaterials. More than 500 papers have been published, and the publication was cited by others for more than 50,000 times. So let's welcome Professor Shi for the presentation.
Many thanks for your introduction, and many thanks for the invitation to this workshop to celebrate the 85th anniversary of PolyU. The title of my presentation is Electrochemical Synthesis coupled carbon dioxide reduction and hydrogen evolution. I'm Jianlin from Shanghai Institute of Ceramics, Chinese Academy of Sciences. You know, with the increase of the carbon dioxide emissions, the temperature of the on Earth is increasing continuously. Nowadays, you know, China is the country of the fastest carbon dioxide emission increases due to the fast development of China. So now people are seeking for carbon dioxide peaking and neutralization. And actually, in China, about 85% of the energy consumption is from fossil energies. And the carbon dioxide emissions in China is mainly contributed by industrial process and the power plant. And what the electrochemistry can do for the carbon dioxide emission peak and neutralization? This is the bigger questions nowadays in China. It seems that the first one is okay. The first one is zero carbon electrochemistry. We start from the clean energies. It must be the to produce to produce green electricities. Then use such green electricities to generate green hydrogen, and people can use this green hydrogen to do a lot of things in industries and in household. And also, sorry. And which can be realized by some industry process, for example, by using electricity, by using electrochemistry process to produce ammonia, for example. And also in the area of electrochemical carbon reductions, people can also use clean energies to achieve carbon capture and carbon reductions for synthesis chemicals and artificial fuels. So I think that there are main 2 trains in the carbon neutralization by using electrochemical process. One is the hydrogen production for zero carbon dioxide emissions. The typical is the hydrogen evolution reactions by electrocatalysis by water splitting for substitution for the fossil energies. Second one is capture and removal of already emitted carbon dioxide in the atmosphere. We use electrochemical reduction of carbon dioxide. The main issue now in these 2 kinds of reactions, carbon dioxide reactions and hydrogen evolutions, One is, of course, at the cathode itself, to how to reduce overpotential of electrocatalytic carbon dioxide reactions and the overpotentials of hydrogen evolution reactions. Next, the second one is even more important, is at the anode. You know, in company with the carbon dioxide reactions and HER, it is the OER, oxygen evolution reactions. Such reactions need very high potentials. Theoretically, it is about 1.23 volt. And also, we need some overpotentials. That means a lot of energy will be consumed in the OER at the anode. And then we can get oxygens. This is of low value, and there also a risk of explosion of the mixed hydrogen and oxygens. So our strategy can be paid to, both on the cathode and anode. For example, at the cathode, we try to synthesize suitable catalysis to lower the overpotential of carbon dioxide reactions and HER. Second, we think it is more important to try to realize so-called electrosynthesis to substitute for OER, and also to promote the carbon dioxide reactions or HER. Okay, we will first pay some attention on the electrocatalytic synthesis coupled carbon dioxide reactions. Anyway, before we talking about the electrosynthesis coupled carbon dioxide reactions, we first pay some attention on the cathode to try to reduce overpotential for the carbon dioxide reactions by using suitable catalysis. For example, in the early days, we synthesized tin nanoparticles loaded on carbon nitrogen matrix to catalyze the carbon dioxide reactions to the formic acid. This is the materials, and this is some catalyzations. And this catalysis shows moderate activities for carbon dioxide reactions with Formate Faraday efficiency of about 92%, with others being carbon monoxide and hydrogen. And it shows a relatively low current density of about 4 milliampere per centimeters. Then the activities can be enhanced by using carbon matrix instead of carbon nitride matrix. This material shows about 100% Faraday efficiency for formic acid without the production of carbon monoxide and hydrogen. And the current density can be much higher. Also, most recently, we synthesized bismuth nanosheet as a catalyst for catalyzing the carbon dioxide reactions. This material shows also a high Faraday efficiency for the formic acid formation. It is about above 99%. And if we set up an electrolyzer, you know, at the anode we can produce oxygen, and at the cathode the carbon dioxide can be reduced to the formate or formic acid. With the Faraday efficiency in this electrolyzer is about 94%. Next, we will move to the anode strategy. How to realize the synthesis of chemicals at the anode to substitute for common OER process in coupling with the carbon dioxide reactions. Here we use tin oxide catalysis. It's loaded on carbon chloride, and this catalysis is for catalyzing the carbon dioxide reactions to produce formic acid. This shows relatively good activities for these reactions. And then at the anode, we use copper oxide nanosheet loaded on carbon fibers, and this material is used to oxidize methanol to formate. That means we can use methanol as the substrate to substitute for the OER process, and then we can also obtain formate at the anode. This material shows also relatively high activities. It shows a reduction of the potential by 208 millivolt by adding methanol compared to the electrolytes without adding methanol. And then we establish an electrolyzer by using tin oxide at the cathode and copper oxide at the anode. And this electrolyzer shows indeed good performance. It shows that the flood efficiency at the cathode is above 90%, and at the cathode and at the anode, this efficiency is above 80%. And you can see that we can synthesize formate from both anode and the cathode. That is a co-production of these chemicals from both electrodes. Okay, let's have a very brief summary. You know, the carbon dioxide reaction potential can be reduced and by using suitable catalysis, and the overpotential reduction and the conductivity elevation is very beneficial for enhancing the carbon dioxide conversions into formate. And at the anode, we can use methanol oxidation instead of OER to achieve much reduced power consumptions. Next, I will focus on the catalytic synthesis coupled HER. First, also similarly to the situation of carbon dioxide reductions, we first pay some attention on the cathode strategies to reduce overpotential of HER. First, about 5 years ago, we synthesized molybdenum carbide. It is used as the catalyst for the OER. This shows morphology of materials, and these materials show the moderate activities. The potential is about 160 millivolt. It is not very low, but it is okay. Not also not very high. It shows fair activities. And I should point out that this experiments was conducted in acidic media. And then the activity can be enhanced by doping some kinds of metal ions, for example, nickel ions in the molybdenum carbide. And these materials showed a little bit enhanced activities. The potential is lowered to about 124. And this material shows better high activities compared with undoped molybdenum carbide. And most recently, we also synthesized a noble metal loaded tungsten oxide nitride, such a composite catalysis. And we use ruthenium as the noble metals. And surprisingly, that this kind of catalysis shows the high activities in the whole range of pH values. That means both in the acidic and in the neutral and alkaline mediums, these materials show the reasonable and very high activities, especially in the alkaline mediums. It shows extremely low overpotentials of only 16 millivolt. It is much lower than that of platinum. It is a benchmark catalyst for HER. And the theoretical calculations show the whole mechanism and why these materials show enhanced activities, especially in alkaline, even much higher than much higher than platinum. In the acidic electrolytes and in the non-acidic electrolytes, the reaction pathways can be figured out by the calculations and suitable reasoning. And most recently, we have synthesized a very special kind of biometallic carbide catalyst, is cobalt tungsten carbide. it's a very special formulation of carbon-6, tungsten 6, and 1 carbon. And the calculation shows that these materials have potential activities for HER. And this is the structure of the materials, and this is the morphology in the TM images. It shows very well crystallized structures and well defined morphology. And these materials shows excellent electrocatalytic HER performance in alkaline. It shows overpotential of as low as 48 millivolt at 10 milliampere per centimeter square meters. And the Tafel slope is as low as 41 millivolt. It shows relatively high activities for HER. And then another advantage of this material is very high current density output. For example, at about 150 or 190 millivolt, the current density can be as high as 500 and 1000 milliampere per square meters at 70 centigrade. And these materials, we think it is very hopeful in the future in industrial use, because it is very active and can produce very high current densities. So let's have a very brief summary about HER strategies as the cathode. So we can enhance hydrogen production by using suitable catalysis. However, you can see that the overpotential for the HER is relatively low. For example, about several tens or several hundreds millivolt. This overpotential is not very high, and actually, you know, the OER overpotential is much higher. So even you can lower the overpotential of HER, there will be less contribution to the energy consumption reduction. So now next, let's pay attention to the anode. How to using, for example, sacrifice agents to replace the oxidation evolution reactions to lower the overpotential and to lower the energy consumption in the whole process of HER. Of course, the catalysis is the most important for the anode process. For example, here we use a kind of morph. It is cobalt and copper co-doped morph nanosheets. This material shows as a nanosheet nanostructures, and then we add methanol in the electrolyte. By methanol oxidation to substitute for conventional OER process. And we can see that by adding methanol, the overall potential can be reduced by about 130 millivolt. This is a very significant reduction of overpotentials. And this materials also shows very high flood efficiency of about 100% for methanol oxidation and the very low Tafel slopes. And you know, we use methanol. So how the hydrogen production, where it come from? Where the hydrogen come from at the cathode? It is from the methanol reforming, or it's from methanol oxidation assisted water splitting. Okay, by using different kinds of solutions, we use some kinds of isotope labeling, and we can have a conclusion that the hydrogen is produced from water splitting, not from the methanol forming. And the methanol oxidation can promote the water splitting. So that is clear that hydrogen is still from the water. So a previous study shows that small organic molecules can be used as the sacrifice agents to substitute for OER. In this way, we can achieve much reduced overpotentials and much reduced energy consumptions. However, in this experience, we use the sacrifice agents, and then sometimes we can obtain carbonate. This will this kind of products will impede the continuous electrocatalytic process. So next, we tried to have some electrosynthesis at the anode. Not only substitute for the OER, also we can get some valuable chemicals by the oxidation at the anode of some kind of small organic molecules. Okay, here is our schematic. At the cathode, it is a common HER process by water splitting. And at the anode, we try to achieve controlled organic molecules oxidation for the electrosynthesis of some kinds of chemicals. Yeah, here example, we try to use glycerol. Glycerol is a kind of it is used as a substrate. Glycerol to substitute for the water oxide to substitute for the OER, and we also then we can by the oxidation of glycerol we can obtain Formate as the product, and in this process we use catalysis. It is nickel-doped molybdenum nitride nanosheets. This nanosheet is loaded on carbon cloth, so we call it nickel molybdenum nitrogen CFC. And this kind of material shows flake-like morphologies, and it's a very shows very high surface area. And you see, you can see that by using this kind of materials as the catalyst at the anode, and by adding glycerol as the substrate for its oxidation to replace OER, we can see that the overpotential at the anode can be reduced by as large as 270 millivolt, and the surface slope is also relatively low at 87 millivolt. And then we can see that during the process, we can obtain the Formate from the oxidation of glycerol. And then we have probed the whole reaction pathways, and by using carbon 13 isotope labeling technique. And this is the whole the electrocatalytic pathways of the oxidation of glycerol to finally to Formate. I will not go to much details of this process. And then we also use this kind of catalysis as the cathode for OER. That means these materials can be used as the catalyst at both anode and the cathode. At the anode, it shows also relatively high activities for the OER. And then we establish two electrode systems for the electrolysis of water and glycerols. And use this electrolyte, you can see that the potential voltage input can be reduced by about 320 millivolt. And also it shows very high Faraday efficiency. For example, at the anode for HER, the Faraday efficiency is as high as 95%. And at the anode, in the alkaline medias, the Faraday efficiency for Formate is about 100%. It is indeed very high. So anyway, the above catalysis is used in the alkaline medias. What about in acidic medias? You know, in acid nowadays people are trying to using acidic electrolyte to realize HER, because in acidic PM electrolyzer people can obtain enhanced HER efficiency and lower the cost. However, the problem is the catalysis. People only can usually use noble metal catalysis in the acidic mediums, because common metal oxide, non-noble metal oxide catalysis is not applicable in the acidic media. For example, manganese oxide can be dissolved in acidic media. However, we found that by adding some kinds of organic molecules, for example, glycerols, and this kind of metal oxide catalyst can be stabilized, not be dissolved in the acidic electrolytes. It shows that first it shows that it enhanced activities for the oxidation of some kinds of substrate. For example, here we use some kind of alcohol. And what is interesting is that it shows very, very durable performance. For example, here we have performed for longer than 800 hours without any sign of activity reductions. And the potential can be reduced by about 170. Why? Why is this kind of metal oxide? It is usually soluble in acidic media. Why this kind of catalyst can be very stable in the acidic media after in the presence of some kinds of organic molecules? We have probed these materials in the production of Formate in coupling with platinum lattice at the cathode, and it shows good performance, and the Faraday efficiency for the Formate is about 60, and also there are some other kinds of products. And then we probe the mechanism why the material is stable, because it is protected by the added glycerol in electrolyte. And we found that what kind of organic molecules can be used to protect the manganese oxide catalysis. We found that the alcohol molecules with multiple and adjacent hydroxyl groups, these kind of materials can be used to protect the catalysis without dissolution in acidic mediums. And we also found that several kinds of other kind of alcohol molecules with multiple and adjacent hydroxyl groups is usable in this kind of electrocatalytic process for the HER and for the Formate productions. Other kind of alcohol molecules is not functional, is not usable in this kind of system. And then we can see that the above electrocatalytic process is always to oxide glycerol to the Formate. It is from C3 to C1 to C. It is possible to realize the electrosynthesis without carbon-carbon bond breakage. That means if it is possible to from C3 to C3 or from C2 to C2 without breakage of the carbon-carbon bonds. Here we see, for example, we synthesize a kind of noble metal net alloys is platinum and silver net alloy loaded on nickel form. And we realize oxidation of glycol to glycollic acid without the carbon-carbon debonding. Yeah, here shows that by using this kind of catalysis, by adding glycols, you can see the potential reduction is very significant. It is the potential reduction can be as high as 980 milliwatts. It's about 1 volt. It is indeed a very remarkable reduction of potentials. And the Faraday efficiency for the glycolic acid production is 92%. It is indeed high enough. And it also shows very high stabilities in the electrocatalytic process. And then we have established electrolyzer for the hydrogen production and for the glycol oxidation to glycolic acid. it is shows 100% Faraday efficiency for the HER and 90% Faraday efficiency for the glycolic acid production at the anode. And here, then we also plot the mechanism why this kind of nanoroid shows enhanced activities for the glucose oxidation. Finally, I will try to show example of the co-production of the hydrogen from both anode and the cathode, in addition to the chemical synthesis at the anode. You know, commonly people produce hydrogen and oxygen by water splitting. And I also introduced just minutes before that we can use small organic molecules by small molecular oxidation to produce some kind of chemicals to substitute for OER and in coupling with HER. And then nowadays we can not only to synthesize some chemicals at anode, we can obtain hydrogen from both cathode by HER and also hydrogen from the anode. Here is some chemical reactions we can use, and here we have choose this kind of alcohols. It is alpha hydrogen ion alcohols, 1,3-propanol diol. We call it 1,3P. And by using this kind of alcohols, and we use palladium, bismuth, and alloy catalysis, and we can realize co-production of hydrogen from both anode and cathode, in addition to the anode chemical productions. Okay, here shows that by using this kind of catalysis, the 1,3P molecules can be oxidized at a much lower potentials. The potential reduction can be as high as 1 volt. It's indeed very high. Then we can produce a very special kind of chemicals. It is called hydroxyl propionic acid, and this is also very high value added products by the oxidation of 1,3P. And here we have probed the whole chemical reaction pathways during the electrocatalytic process. And I can tell you that all the alpha hydrogen was utilized to generate hydrogen at the anode with 100% Faraday efficiency, in addition to the hydrogen production at the cathode. And besides, we also can obtain some kind of chemicals at the anode. Okay, here we see that some kinds of several kinds of alcohol molecules with alpha hydrogen ion structures can be used to produce several kinds of chemicals, in addition to the hydrogen production from both sides. Okay, let's have a very small summary and outlook. Anyway, the electrooxidation of small organic molecules to substitute for OER, it shows much remarkable reduction of potentials and energy consumptions for the both HER and carbon dioxide reactions, and also no oxygen will be generated at the anode, and instead we can obtain value-added chemicals at the anode. And you know, here is our very brief summary that commonly we use water oxidation to produce hydrogen. Then we can using sacrificing agents to assist HER, and also we can using electrosynthesis to couple HER, in addition to the chemical synthesis at the anode. And not only HER carbon dioxide reductions or nitrate reductions, we can to couple many kinds of chemical reduction process to produce diverse products at the anode. Finally, I would like to thank you all for your attention to my presentation. Thank you. That's all.
Okay. Thank you very much, Professor Si, for your very enlightening talk. And now it's time for the questions. So for the audience, you can either type your questions in the chat, or you can turn on your audio to directly ask. Maybe I ask the first question. So, Professor, I see that you have shown a lot of technical route for the carbon oxide reduction into different chemicals. So I'm not in this area, so I'm just wondering, so which technical route is the most promising for the future? Because I say you can transfer into different chemicals.
Thank you. Anyway, not only for the carbon dioxide reduction, also the HER. The most technical point is to find suitable catalysts. This is the first one. The second one is to find suitable organic small molecules. Currently now we use small alcohol molecules to as the substrate for its oxidation at the anode to substitute for the hydrogen to the OER to the oxygen evolutions. That means yes, the catalysts and the small organic molecules are the two factors, very important factors.
Okay. Thank you.
Professor Shi, thank you for your very enlightening talk. So I just have a very small question, a short question. In your last piece of your work, you produce hydrogen from both anode and cathode. So I'm just wondering, what is the cost of the small molecules you used in your experiment?
You mean the cost?
Yeah.
Of the small molecule. At the present, we do not pay too much attention to the cost of the small organic molecules. Anyway, we found that after the oxidation of this at the moment, after oxidation of this kind of molecules, 1,3-propanediol, the product is value added. This is certain. Yeah, it's value added.
Okay. Thank you. Yeah, very nice talk. Thank you.
Thank you.
Okay, so we still have time for another one or two questions. Okay, maybe I ask another question. So in this slide, so Professor showed that we can have the hydrogen from both the anode and the cathode. So we know normally we get the hydrogen from the HER. So here we get it from both sides. So from which side is more preferred?
Commonly people perform HER by water splitting.
Yes.
Yeah, and why at the anode the hydrogen is from the organic molecules. It we call the alpha hydrogen, and it depends on the number of the amount of alpha hydrogen atoms at the molecules. I haven't paid less attention on at which side the hydrogen production is more productive. I will check it. Thank you.
Okay, thank you very much.
Thank you.
Okay, so due to the time limitation, so we stop here and then we move to the second speaker. Let's thank Professor Shi again for the wonderful talk.
Thank you.
Okay, thank you.